Hi guys, so this is the recording for the lab lecture for this week, which is we're just going to take a look at some more advanced crystal structures. We looked at simple cubic crystal structures in our lecture, but we're going to go a little bit beyond that. And these crystal structures, as you can see from these diagrams, they exist in nature. These are mostly ceramics, which exist in different crystal structures of different kinds, and then we'll also talk about put some examples. All right. So the one thing that we did not speak about in our introductory lecture was the fact that all crystal structures are related by the fact that there is some form of symmetry which is taking place, right? And what's the definition of the symmetry? The hard definition of it is that a body is said to be symmetrical when it can be divided into parts that are related to each other in certain ways. The operation of transferring one part of the position of a symmetrically related part is termed a symmetry operation, the result of which is to leave the final state of the body indistinguishable from its original state. In general, successive application of a symmetry operation must ultimately bring the body actually into its original state again. So what that means is by these symmetry actions, which can be reflections, translations, and other things, you repeat. It's just a way of how the unit cells can be repeated to come up with the overall structure. And in order to follow and create these crystal structures, these rules of symmetry have to be followed. So it's basically the set of mathematical rules that ends up describing the shape of an object. And I would encourage you guys to go and read the textbook in chapter 3 to understand what symmetry is and what these symmetry operations are. An example of an object with a perfect symmetry, right? What do you think is an object that has perfect symmetry? It's a sphere. And why is it? Because it has infinite planes of symmetry that pass through its center. And it has, along with those planes, it's also got infinite number of axes about which you can rotate it, and it always remains the same, right? Nothing's changing in the overall shape, right? So now if we go back to our lecture, when we started looking at the crystal coordinates and the directions and the Miller indices for the planes, we had said that these rules apply in general for all crystal structures, right? But we'd only been looking at cubic crystal structures in our case. And the reason for that is that the generalized unit cell is not a cube. It has 3 different dimensions, and it also has 3 different angles. So a generalized cube always has A, B, C, and alpha, beta, and gamma. And it's those coordinates and directions that we saw are generalized so that they can be consistent for all the crystal systems and crystal structures, right? So where do these crystal systems arise from? They arise from the fact that all the different possible combinations of A, B, and C, and alpha, beta, gamma, they result in basically 7 different combinations that you can end up having. And thus, you have 7 different crystal systems, and crystal structures form subsets of those systems. For example, the one that we looked at in our class, and these crystal systems are defined in order of decreasing symmetry, right? So there's a limited, the number of operations that you can do to repeat the unit cell and make the whole crystal structure keeps decreasing, right? So what does that lead into? That leads into the fact that you have these 7 different crystal structures that result. And as you're going from 1 to 7, so you have 1 is cubic, 2 is hexagonal, and these are the 2 that we'd seen, right? Because cubic was simple cubic, was face-centered cubic, and was body-centered cubic, and hexagonal was the hexagonal close pack structure that we saw, right? So cubic, for example, is a crystal system, and within the system you have different crystal structures which can be, and the examples that we'd seen were simple cubic, were body-centered cubic, and face-centered cubic, right? And then you go beyond, and as things keep changing, as those ABC keeps changing in relationships to each other, and alpha, beta, gamma keep changing in relation to each other, you get tetragonal, rhombohedral, which is also called trigonal, orthorhombic, monoclinic, and triclinic, right? So in general, there is a decreasing amount of symmetry as those things, as ABC and alpha, beta, gamma are changing in relationship to each other for these different crystal systems, right? So if we look at the cubic system, which is the most symmetric, right? Because if you go A in the X direction or A in the Y direction or A in the Z direction, you're doing the same thing. So it's a very symmetric thing. And basically that's what symmetry means in crystal structures, right? So if you can get the unit cell to repeat itself in the same way in different things, then it's in different directions. In just the case of translation for this case, then you have more symmetry in the crystal structure. So the cubic system is the most symmetric, and the ones that we saw were simple cubic, were body-centered cubic, and face-centered cubic, right? And what's happening over here in terms of our generalized unit cell? In terms of our generalized unit cell, all the unit cell edge lengths are the same, and they're all squares, right? So the angle, alpha, beta, gamma, all of them, all the angles is 90 degrees, right? And the examples of these are diamond, gold, pyrite, and silver. And we're looking at ceramic examples, so kind of like those crystals and minerals which form crystal structures that you see in nature, right? The next one is the hexagonal or the HCP structure. So the hexagonal system has an example of the HCP structure, which we had seen last week, we know and love. And we'd seen from there, the way that you get the unit cell is that you've got to take a third, and we'd seen in the example problem that we did in class. And what's happening here is that if you're looking at this bottom face over here, right, you have A and A, which are equal to each other. So A equals B in this case. And then you have the third dimension C, which is the height, which is different from A, right? And then you have alpha and beta. So you have two 90-degree angles. So you have one 90-degree angle over here, and you have another 90-degree angle over here. But then you don't have a 90-degree angle in between. So that's 120 degrees over there, and then that's going to be 60 degrees over there, right? So you have gamma, which is basically equal to 120 degrees, right? So basically C is different, and then one angle is different, right? An example of the HCP structure in terms of the ceramics that we're looking at are beryl, emerald, morganite, and zincite, right? And then now we go on to things that we haven't seen before. So the next one is the tetragonal system, whereby A and B are the same, so they have the same length, but C is different, and all the angles in here are 90 degrees still. So it's basically you have a square base which is just elongated in one direction. And examples of this are rutile, zircon, and my favorite name for minerals, wolfenite. This sounds so like you know, like very animalistic. Wolfenite, yeah, like Vikings, strong. Get it? Anyways, all right. And then after that we have the trigonal system, whereby what's happening is that all three sides of the unit cell have the same length. So we just call that A. And then you have all three angles within the unit cell now are not equal to 90 degrees. And the examples of these, this system is, you see amethyst, calcite, and quartz as well. And then you have the orthorhombic system, which is basically you have all the angles which are 90 degrees, but the base, no matter which way you look at it, has unequal sides. So you have A not equals to B, not equals to C, but you have the three angles which are equal to 90 degrees. And examples of these are celestite, topaz, and alexandrite, right? And because of simple mathematical assumptions, you have a couple of assignments to do with this orthorhombic system. Then you have the monoclinic system, which is also new, where you have all three sides are different and two angles are 90 degrees, but they're not equal to this third angle. So this angle here is equal to 90 degrees, and that angle there, or that angle there, is also equal to 90 degrees, but sorry, not that angle, but which angle is 90 degrees? So you have that angle being 90 degrees, and I believe So this angle is not 90 degrees. That's the beta, and then this angle is 90 degrees, right? And the example of this is azurite, mica, and serpentine. Then you have the triclinic system, which is none of the sides are equal to each other and none of the angles are equal to each other or equal to 90 degrees. So nothing is the same. And this is the least symmetric system, right? If you repeat it in unit cell edge lengths in just simple translation, you're getting different forms, not different forms, but it doesn't look the same if you were to repeat it in another direction. So it's the least symmetric. And examples of this are amazonite, kyanite, and rhodonite, right? And this is the least symmetric system, right? So you have example problems to go through and a couple of assignments in this lab. So make sure that you go through those. And if you guys have any questions during this week as you are doing this assignment, please let me know. All right, guys, a wonderful weekend, and I will see you guys on Tuesday in the class or earlier if you want to hang out and ask some questions about the assignments, about the lab assignment or the homework. All right. And yeah, there's a lot of information on the internet with crystal structures and crystallography as well. So feel free to go out and do some additional reading if you guys want to, or if you need some, if you're interested, I can just email me and I can forward you some links as well. But the textbook is the best place to start. And I would start with understanding what symmetry is and how that relates to crystal structures in order to get a better understanding of how these different crystal systems are forming. All right. Thanks, guys. Cheers. Bye.